Okay, so let's talk about some of the things that the theory of relativity predicts will happen because the speed of light has to be the same for all observers. That's one of the main tenets of the theory of relativity, is that the speed of light has to be the same for all observers. Which is kind of crazy to think about because if you can imagine, that's like basically they're saying there's something out there that we all have to measure at the same speed no matter how fast we are moving. That's like saying that this baseball is thrown at a certain speed and everybody measures that same speed. Now, with the speed of light, because it's a constant, generally represent it with the letter C for constant. All right, so we can imagine this baseball is moving at a constant speed, that everybody measures the same thing. But how can everybody measure the same speed with all of these relative velocities in here? You know, the orange arrows show the perspective of the orange car, your friend driving the orange car. Let's say this is you in the house. From your perspective, all of your measurements are in green. So you see your friend moving to the left at 40 miles an hour and your mom moving to the right at 20 miles an hour. And then your mom, who's driving at 20 miles an hour, sees you out her window moving to the left and your friend moving even faster. Now, how can everybody agree on the same speed? Well, let's talk about what a speed is. Here I have it measured in mph, miles per hour, which can also be written as a fraction. Miles per hour. Miles over hour. But it doesn't have to be miles, it doesn't have to be hours. Really, it's going to be distance over time. Any kind of a distance measurement, feet or inches or centimeters, over any kind of a time measurement, and that'll give you a speed. So you can go in meters per year or inches per minute. Any of those would work. They're all different kinds of speeds. All right, so distance over time, and that is basically how we measure speed. So how can three different people with different perspectives measure the same time? I think a good analogy is to think about just fractions and how different fractions can actually equal each other. So 1 over 2 is numerically the same as 2 over 4, which also ends up equaling 5 over 10, because 5 is half of 10, 2 is half of 4, and 1 is half of 2. So the ratio between them, the proportion, stays the same. We can say that all three of these are equal. So you can see that if we made the top bigger here, then we would have to, in a proportional way, make the bottom bigger so as to keep these equal. Now the same thing happens with relativity. So let's say that you measured your own time in green, distance over time actually, d over t, but that also needs to equal the distance over time that your friend measures. So his orange distance over time, and that needs to equal, all of these need to equal each other, the distance and time that your mom measured. So with these proportions, these all need to add up to the same number, which is going to be that constant of the speed of light, c. So here, if you can imagine these three ratios being kind of like these three ratios, you can see that when we adjust the top of one, it's going to have to adjust the bottom as well so that the overall speed will stay the same. So how can distance and time actually change? Well, if somebody is moving relative to you according to the theory of relativity, then time will be dilated. Time dilation. Time gets changed. It actually ends up being slower. Time dilation is in effect. And also length contraction. These are the two effects of relativity that we'll be talking about today. There are actually others, but these are the two big ones that we want to try to wrap our minds around first. Time dilation and length contraction. Okay, so first, time dilation. How can time be different? Well, let's say that here's your clock, and it is moving at a normal speed of 1 tick per second. Now, according to relativity, if anyone's moving relative to you, then you will see their clocks moving slower than yours. So this is your view of your friend's clock, so it's in green, but it is slower. And actually the same with your mom too. Your mom, if you see the clock in her car, it is slow compared to yours. But it's actually true in the reverse, because if your friend sees your mom moving to the right at 60, but she sees him moving to the left at 60, with relative velocity, everyone's perspective is equally relevant. There is no absolute rest or reference point that we can measure from. From your friend's perspective, then, his clock is normal because he's not moving relative to himself. He's always where he's at. But your clock is slower than his, mind-bendingly enough. So it doesn't matter who's moving, but from your perspective, if someone is moving relative to you, then their clock is slower. It takes more time for a second, or another way to think of it is that in the same time that you measure something, less time will have happened for them. And this is an actual phenomenon. It doesn't just look like it. This is actually happening. But how can it be true for both sides of the picture? It is true, but is one of them going to be right? Because they can't both be right, can they? According to the theory of relativity, yes, they can. In fact, this is what happens, that anybody moving relative to you will have their time going slower. The other thing that happens is length contraction. So let's look at the length of your yardstick. You have a yardstick, and it is 1 yard. Now, your friend also happens to have actually drawn a yardstick or painted one onto his amazing car, but his yardstick is noticeably smaller. Now, you know him to be a meticulous fellow, so he didn't draw it on wrong. But actually, length along the direction of motion gets contracted so that the measurements for the speed of light can come out to be the same. So if the amount of time passing is less, then the distance measured also has to be less in order to keep that ratio true. What about your mom? We didn't really look at her. Her yardstick will be a little bit longer than your friend's because she's not driving as fast, but it also will not be as long as yours because you are not moving relative to yourself. So her yardstick, she didn't actually paint one on the car, she just happened to tape one there to protect the paint. So her yardstick is going to be shorter than yours, but not nearly as short as your friend here who's driving faster. Now, the same thing is true, though. From his perspective, his yardstick is still actually a full yard. And your yardstick is the one that is shorter, 1 yard. And your mom, who's moving even faster relative to him, her yardstick is the shortest of all from his perspective, 1 yard. And that's the basics of time dilation and length contraction. The two main effects of relativity is that when someone is moving relative to you, time will be going slower and distances will be measured as shorter. And that's all so that this ratio can be protected and that the speed of light comes out the same. Now, why don't we see that in everyday life? Well, that's because the speed of light is actually a crazy big number, 3 times 10 to the 8th meters per second. But that's not a normal number that we work with, so let me spell it out for you. That's the same as 300 million meters per second. That's how fast the speed of light is. Now, in order for you to see relativistic effects, you'd have to be going a pretty significant percentage of the speed of light. So, I mean, even if you were going 10% of the speed of light, that's going to be 30 million meters per second. And you would not see much for relativistic effects because it's only 10% of the speed of light. So we don't see these effects on an everyday scale, but they are true nonetheless. They have been proven by experiment. And then in the next video, we will do some calculations then to see exactly how much things get contracted or dilated based on an actual speed that someone is moving at.